So, oh yeah, I sent you a meme.
Oh yes, so it's the what my friends think I do, what other people think I do, what I think I do, and what I really do meme. So what my friends think I do has got Isaac Newton sitting under an apple tree being very pensive, thinking about the state of the world and really, big, high, grand concepts. What other mathematicians think I do has got Alice in Wonderland sitting around at the tea party, being wild and crazy. And, so I think that sounds pretty accurate. this is pretty out there in terms of math. What I think I do is got a very stodgy professor sitting in a very high backed chair.
The architect from The Matrix. So it's The Matrix, the second movie, right? But this guy is the architect of The Matrix. He's the person who created the entire simulation of The Matrix, and maybe a simulation inside a simulation.
So you think that you're building up simulations inside of simulations and these big grand structures of categories.
The universe. I can see the universe.
Building up the universe from first principles of mathematics in your head.
Yeah, it's kind of like a lot of like the Eugenia stuff of the mathematics of mathematics, thinking about thinking, and it's kind of like grandiosity, let's say,
Yes, and then what I really do has just got Robin Hood ? Shooting like 6 arrows at once.
Yeah, so that is Mel Brooks. I think it's Robin Hood Men in Tights or something like that.
Oh, yes. That's a funny movie actually. I like that.
And so the thing is, basically most of the time you're just fucking around with arrows.
So I guess I should introduce the podcast now. Hello, everyone, and welcome to another episode of In Plain English. I am your host, Jamie Moffa, and today we are recording in person from my living room. It has been wonderfully set up by my partner, Max, who dabbles in audio engineering when he isn't doing real engineering. And for this momentous occasion, we are going to be talking about math.
Don't sound so sad.
No, it's going to be fun. We're going to be talking about a few chapters from the book The Joy of Abstraction by Eugenia Chang. It is actually like really cool. She does a really good job of explaining mathematical concepts in ways that can kind of be understandable by someone who's not a mathematician. And I am not a mathematician. I went up to Calc 2 and I was like, sequences and series are getting too much for me. We got to cut it off here, man. But who is a mathematician is Will. Will, would you like to introduce yourself?
Hello, yes, I am a mathematician. I have a fancy schmancy PhD on category theory. So I think I'm somewhat qualified to talk about this.
Wait, this is a real thing? I thought you were just giving us black magic to research. You can get a doctorate in this?
You can. Yeah, I actually got my PhD the same place that Eugenia Chang got her PhD. So we both came from the sort of like same institution, right? For our graduate studies, we studied with like the same people basically, but she was, I think a generation before me, right? And so, I did my master's in category theory, did my PhD in category theory. I've talked, I think 3 times at the International Category Theory Conference. Wow. And now I am here to talk to you fellas. I feel that the categorical approach is that it's the dialogue that matters. Do you get me? It's not just me. It's like your questions and everything else.
Which is why we're here sitting around a jerry-rigged recording studio. Dialoguing with our 2 non-expert guests, Max and Parker. So Parker, do you want to go ahead and introduce yourself first?
Yeah, I'm Parker. I definitely do not have any math degrees. But I'm excited. After doing the reading, I never really thought about like how math talks about relationships. Mm-hmm. So I'm excited to talk about it.
Yeah, and Max.
Hello, I am Nicholas Max Wolslegel, and for the amount of math classes I've taken, it's quite humbling to be in a room where I am not a math expert. But I took the bare minimum required to get an engineering degree, which is many classes, but no degrees. And I'm being traumatized freshly. So this will be a bonding experience for all of us. If I start crying, just slap me.
So, do we want to talk about all of this math that we just had to subject ourselves to?
Sure, I can talk about the book. I can talk about what's not in the book as well. Because I think Eugenia's approach was to try to make it self-contained.
Yeah.
Right? She wanted to have a book where you didn't need to study, do an undergrad in mathematics to understand category theory, which is quite ambitious, And I think she pulled it off, right? But because I think her purpose was to get people to understand how to think categorically, right? But also, I think one of the things that she mentions herself is that we shouldn't study something in isolation, right? We should look at a context. So maybe I could give a bit of the context of like, how did category theory appear on the horizon, right? What is the history behind? Because there's some really interesting stuff there, especially interesting stuff by like a very important mathematician, Emmy Noether, who I find really fascinating, who was the first person to actually do like categorical thinking, So I thought maybe I could start with a bit of like the history of the subject. Would that be okay?
Please.
Yeah, no, that sounds really cool. Yeah.
I think everything starts in 300 BC.
We're going way back.
in Greece, with Euclid's Elements, right, which was the first usage of the axiomatic method, right? Because I mean, what do you fellas think that a mathematician does, right? What do you think a pure mathematician does
right now or in 300 BC? Because 300 BC is adding beans in my mind.
So here's the thing: we're still kind of doing the same thing.
Oh my God, we're still on beans?
Yeah, we've evolved to other categories, I would say, but so a lot of people think that mathematics is about calculations, right? They think it's about numbers and calculations and, all the operations that you learn in high school, right? But pure mathematics is much more focused on proofs, right? So what Euclid did, which was really fascinating, was that he developed the axiomatic method, which is the method that we've been using in mathematics for over 2,000 years. Every time people talk about like how something is not scientific, I can kind of understand why they're talking about that, but like mathematics isn't scientific either. We don't use the scientific method. We don't do experiments. We don't try to verify our theorems by looking at them in the real world. We use the axiomatic method, right? And what is the axiomatic method, right? We just postulate what we consider to be starting principles. Euclid called them, self-evident truths, right? Don't want to go into what truth is right now, right? But first principles, and we derive conclusions through logic, right? And so Euclid axiomatized geometry, and then he would try to, using those characterizations of what is a line, what are points, what is a circle, derive logically all the constructions, right? A lot of geometry was basically all of geometry was using this axiomatic system. I'm not so sure about algebra, but later on now we go to the sort of end of the 19th century, right? Because that's when people started using an axiomatic system for other areas of mathematics that were not just geometry. Right. And so what we had was a crisis of foundations in mathematics. I don't know if you've heard about this.
No, but when your house has a crisis of foundations, you probably shouldn't be there anymore.
Right. No, because people were coming up with paradoxes. There was Russell's paradox. There was other paradoxes as well. There was like non-Euclidean geometry coming about, right? They were like, whoa, there's more than one geometry. What is the geometry of space actually? Is it the Euclidean stuff? Is this non-Euclidean stuff? And people are kind of worried, like, we can't just go about thinking like, oh no, come on, the real world is mathematical. Come on, mathematics is reflecting the world. They're like, I'm not so sure because one of these non-Euclidean geometries can't be right. They can't all be right, So people started thinking like, what are the foundations for mathematics, right? And there were many different approaches to solving that problem. The one that really sort of became mainstream was making set theory the foundations for mathematics. Okay, basing mathematics on the notion of set and membership. Okay. And I won't get into the other notions, but that's the one that is like the mainstream one. This is why, in a lot of textbooks of mathematics for high school, you talk about unions and intersections and whatnot, But set theory is taught because it's the foundations of mathematics, right? And it kind of like cleared up most of the, cleared up all of the paradoxes. We're like, yeah, we've got like these solid foundations here. None of the paradoxes that we know can interfere with us. And so, we're kind of good for now. Later, so that was the solution to the crisis of foundations. They're like, yeah, we got foundations for mathematics. All objects are made out of sets. And the language that we have is that of membership, right? Around the 1930s, you had a French group called the Bourbaki group, okay, which was a bunch of French mathematicians who got together to, okay, sure, we've set up the foundation, and now let's build the house, right? And they had like this unifying notion of, of what is a mathematical structure along their lines, right? They're like, okay, so now we have sets, but the geometer is doing geometry. The algebraist is doing algebra. The combinatorialist is doing combinatorics. Let's,
and no one can understand each other.
Right? Yes, they wanted to like put everything on a unified format. And so they're like, okay, actually, you're all looking at sets with a specific type of structure. Okay, so the people doing geometry, you're probably, looking at sets with some kind of geometric structure, some kind of notion of distance. So you probably have a function that gives you distance. The people doing algebra, you probably have sets with algebraic operations like adding and multiplying and things like that. So those are, you have your sets with your operations. The topologists are doing things with like, sets which represent sort of geometrical spaces, and your operations are, sort of deformations of that space, right? So they had like kind of tried to unify things, right? So you had this notion of areas of mathematics, and they all come with some kind of structure, right? And some kind of function that preserves that structure. So for instance, if you work in order theory, if you just want to talk about ordered sets, your mappings will be functions that preserve the orders, right? So that things which are, if one thing is greater than the other, when you apply the function, it's still going to be greater it preserves the relation, right? And so it kind of cleaned things up and applied the axiomatic method to most of mathematics, right? But some people were not quite satisfied. Some people wanted to take that a little bit further, because they started realizing that, sure, you describe these structures using first order logic, using a formal language and whatnot. You have this same presentation, but it looks like, sometimes the same theorem is appearing over and over again in different parts of mathematics, right? And they're like, so what's going on there? And one of the people to figure this out was Amy Noether, right? Who was a German mathematician, and she was working mostly, again, turn of the century. And I think her most important theorems were done in the 20s and the 30s. She was in Göttingen, and her story is really interesting. So she was incredibly talented. So Noether's theorems in physics, she has a bunch of theorems in physics, are considered like some of the most important things in physics, right? I don't understand them because I'm not a physicist, but I know that she was working with things very closely related to like what Einstein was doing, and actually, I heard one story that she was actually volunteered to sort of work with problems that Einstein couldn't solve, that he was getting stuck on the mathematics, and so they passed it on to Amy Noether, right? She was not allowed to lecture in Göttingen because she was a woman. And then what happened was the leading mathematician there was David Hilbert. He would just announce classes under his name, but she would lecture, right? And he was pissed off at this. I think they were saying like, oh, what will our soldiers think when they come back from the war and there's a woman lecturing them?
Oh, no. Because that's the biggest of their problems when they come back from a war, is having a woman professor.
And then David Hilbert's reply is like, I don't know what you're talking about. This is a university, not a bathhouse. And so she was lecturing there like anonymously, not anonymously, like she was like undercover, right? Eventually, like they really like pushed to get her to be hired by the department. Eventually they did hire her, but no salary. Like a very, very bad, pay gap there. And then eventually she was able to get a salary, and she was the lowest paid person in the entire faculty. Right? And this is one of the most important persons in mathematics, right? The person who kind of kickstarted category theory, and sort of what I would call like a structuralist approach to mathematics, right? Which is what I'll try to describe now, right? Because people were noticing that, certain objects, you had two different objects that had kind of like very similar properties, and they were almost indistinguishable. So here's an example, right? We count using natural numbers like 1, 2, and 3, right? But if you learn any programming language, you know that they start counting from 0.
Sometimes.
Right?
Well, you should. Languages disagree on this, but there is a correct answer.
So that's the thing. Some do and some don't, right? And you're like, oh God, why do you start counting from 0? Why don't you just count from 1, right? But the thing is, it doesn't matter, right? If, you start counting from 0, you start counting from, what matters is the one that comes next. The one that comes next. What matters is the kind of structure that you have there in the numbers that you're using. And so this is, again, another ongoing debate among some mathematicians. Does the natural numbers have 0 or not? I think it does. But there are people who go like, well, but I've never seen 0 cows, grazing in a field. And I'm like, yes, you have. When the field has no cows, that's what you see, right?
I was gonna say I've seen plenty of fields with no cows.
Or a field that has cows, but none of them are grazing.
Right. But anyways, I think you should have 0. But some people think you shouldn't have 0. But honestly, it doesn't matter, right? It doesn't matter because for the purposes of counting, for the purposes of having that ordered structure, it's exactly the same structure, right? The presentation doesn't matter. The labeling doesn't matter, right? What matters is the structure that you have inside each set, right? So there was this kind of idea floating around that, it's not really what is inside the structures that matter, right? It's how they relate to other things that matter, and it's not really the presentations that matter. It's much more like external sort of relational properties that matter, right? Taking that approach, right, Amy Noether was able to sort of look at these theorems that were appearing in many different contexts and sort of find a language to describe them, which was a category theoretical language. She didn't use arrows, but if you just substituted the tildes for arrows, it would be exactly how we do it. So she came up with the language in which to phrase the theorems, and then she was able to make a proof only using that language, and then show that in many different areas you could apply that language, that same language. They had instances of that language there. So basically, she didn't have to go area by area proving the theorem in different contexts. She used a much more abstract setting to make a more general proof, right?
So relating all of this like great the 1900s like reorganizing of math that brought these into these common languages, she was able to say, well, now that we're in a similar common language, if we just take it a little bit farther, we can see how everything's connected here.
Yeah, exactly. But the language that she was using was new, right? The sort of common language that the Bourbaki group used was that of like first order logic to sort of describe the elements of a set, right? Now she was going for a more external approach. I'm not going to describe the elements of the set. No, I'm not going to look into the set. I'm going to describe the relationships of the sets with other sets. And that's where the category theory comes in, right? It's like, it's not opening up an object, it's looking at its relations, right? And I think now is the time for like a fancy metaphor, right? Which is, what is the difference between the sort of structuralist approach to mathematics versus more of an like atomist approach, right? Where you're trying to build things from the ground up, right? And it's the question, and I'm going to steal this from an Oxford professor. His name is Bob Kirker, and he does category theory applied to like quantum physics. And it's a really good metaphor, which is, you can ask yourself, why does a tiger have stripes and a lion doesn't, right? Why is that? Why does a tiger have stripes and a lion doesn't, right? And the sort of set theoretical approach, the atomist approach, would be like, let's open them up and see what's inside. And you open up the lion and you open up the tiger and you see, well, the organs look exactly the same, except for one maybe slightly bigger. You go, let's keep opening. Let's go further into the cells. The cells look exactly the same. Let's just keep going until you finally go into the DNA and you find, haha, I found the piece of DNA that has the stripes and it's not there in the lion. Therefore, I found why the tiger has stripes and the lion doesn't. But did you really? Because you might think, no, the tiger has stripes because of how it interacts with its environment, right? The tiger has stripes because that's what will camouflage it in its environment, right? Yeah. It's its relationship to things external to itself, right, that gives it the stripes, And the thing is, both answers are correct, but it's just a different approach. Yeah. One is the approach of like trying to build it from like atoms, right? And the other one is like looking from the top at the interaction of elements.
Well, and they're also answering a different question. When you're going into the DNA, you're answering more like, how does the tiger have stripes? And when you're looking at the like evolutionary pressures coming from the environment, you're asking, why does the tiger have stripes?
Yeah, exactly, right. Because, I don't necessarily think that the structuralist approach is better, right? I think it answers some questions, right? Because I used to be, sort of like, no, category theory is better than all the rest kind of thing. And then one category theory said, yeah, sure, but you're not building anything. You're not constructing anything, right? You're just looking at relationships between things. A world without set theory, would be an empty world where you haven't built anything. You just, you just look at these relationships, but between which objects built, from a set theoretical perspective, right? And so, yeah, I think it's just two different ways of viewing things, right? But we do like to think that we can see the big picture. Do you get me? That category theory is the one that's really giving the big picture. Whereas, other approaches, are getting sort of lost in the detail and whatnot. I think a lot of it boils down to just like personal preference of how you like to think. If you want to think in terms of abstraction and large concepts, as opposed to very intricate, details, Oh yeah, so I was talking about like Amy Noether, right? But I can continue on to like the actual, beginning of categories, right? Because she did things without actually defining categories, without defining morphisms. It was only around 1945 that the word category theory, the word categories and morphisms and functors and natural transformations came about, because basically a lot of the objects that mathematicians were dealing with were becoming too complicated, right? They were becoming too intricate and detailed, right? I think Eilenberg and MacLean, they were trying to like calculate, count how many holes there were in this weird, almost fractal-like object. Topologists really like counting holes, right? Like a donut. How many holes does a donut have?
One, unless you've made a mistake.
But the mathematical donut is hollow, right? So it's more like an inner tube, right? So there's the hole that you go through, but there's the hole that inner tube has the air in. So like, and those are two different types of holes, right? Does a sphere have any holes? You'd say no, right? But or maybe yes, because there's like an empty space inside it, but there's no holes. Well, but what if you add an extra dimension, right? Because only in two dimensions the circle has no holes, but when you look at a higher dimension, you can go through it
from the top down. Right. So a higher dimension from 3 dimensions, you pass through that. Oh God, I hate this.
When you view a 2-dimensional object from 3 dimensions, you start noticing things that you wouldn't notice if you only lived in 2 dimensions. So what if we took this a step further? How can we understand the 4th dimension from the 3rd dimension, spatial dimension, right? So if you only had 2 dimensions, it's very easy for you to like protect your little castle, right? You just build a wall around it, But guess what? You can catapult something through the 3rd dimension, right? So now I will build a sphere around it. But if we had 4 dimensions, there would be a way of going in, which we cannot visualize.
Or just tunnel under.
Yeah, so there were these mathematicians, they were trying to count holes in these really complicated structures, right? But the
Weirdos.
Exactly. The structures were really complicated, and they were like, no, we can't try to open these things up. They like have like a fractal structure and everything. So let's look at how they interact with simpler structures around them, right? That was their approach, right? And so they kind of borrowed, Emmy Noether's approach and formalized it. They're like, no, actually, we can formalize this. Let's define what a category is, define what a functor is, which is a structure preserving map between categories, and which establishes relations between categories. And let's then go a step further, define what a natural transformation is, which is a relation between 2 different functors, a relation between relations, right? A lot of category theory gets very meta in that sense of like, you're talking the mathematics of mathematics, relations between relations, between relations, right? I think this might have been mentioned in Eugenia's like first chapter of like infinity categories and stuff like that, And that's when they pop into the sort of mathematical landscape. We define what a category is in that 1945 paper, right? And it was mostly just, used by some people doing algebraic topology, where they were trying to take problems in topology and try to use algebra to help them. They're trying to relate 2 different areas, right? And so it was a tool for taking problems in one area and transporting it to another area, see if you could solve it there, right? But then in the 60s, right, this is when a guy called Alexander Grothendieck enters the chat, basically, and like changes everything. And who, again, is another sort of like, in some ways, I don't know if I could call him a personal hero. No, I think there's a bit too much. But a guy I have some admiration for, even though he went insane in his later years, right? He started using the categorical language for now algebraic geometry, which was another area. But he wasn't just trying to sort of translate, things in one area to another. He was using it to actually define objects in his area, right? And then the kind of thing exploded. People started using the category theory language to define things and not just to try to go from one area to another, right? And then it just took off. It went into the direction of like computer science, and then quantum physics, a bunch of different places, and it just like spread the sort of like structuralist approach of like, we're not going to try to necessarily build things, but define them by the relations that they have to other objects, really took off, right? And even though I'm a pure mathematician, right, I did some like research of like what are the real life applications of this, right? And this is something that gets updated all the time, right? And so one of I think the most sort of like solid real life application is the programming language Haskell. I don't know if you've heard of Haskell. It's a functional programming language, very academic language, but apparently Facebook uses Haskell to program anti-spam stuff. GitHub uses it. What else? I made a list here of stuff. Yeah, and the Target stores use Haskell, which is based on category theory. Target stores use Haskell for their supply chain optimization algorithms. So next time you buy something at Target, you know that there was category theory putting it there. Okay.
All right, you've proved that your degree isn't something real. I'll resend that black magic sentence from earlier. I still don't understand how you make a computer language based off category theory or referencing category theory, but that is cool as hell.
Yeah, that's something that I feel I can't talk about.
We need to find a computer scientist.
Yeah, someone who understands Haskell.
I now believe that category theory is out there. It exists. But would you say that like for the average human being that's interacting with this, like it is someone who's not going to get a PhD in this, is it more just, should we interpret it as like a way of wording math, rewording parts of math to read it differently, or is it doing something fundamentally new, right?
So it's a bit of both, right? So the language itself, what it does is that it clears off a lot of the dirt, that a lot of the faff around things, and makes things very, very clear, right? So that's how it becomes so applicable in mathematics, right? You're taking away different presentations and somehow looking at the essence of something. I can get into more details like later, right? But a lot of people joke about category theory, saying that there are no real theorems in category theory, right? There are very few theorems. It's all about definitions. So it's more about sort of using the language to define your objects so that things are very clean, right? And most of the times, I see what a lot of the category theorists do is come up with new definitions and showing like, look, this is a new way to look at this. This is another way of looking at that is incredibly clean. Like, actually, this, a metric space is just this type of category, or a vector space is just this kind of category, and that kind of thing. So they have like categorical descriptions of things,
And that becomes useful because then you can relate it to something that's not that type of category, but is a different type of category.
Exactly. So this more general structure that you can like shift sideways and look at different things, And yeah, so that's kind of like the main use and why a lot of people started using it, because it's so clean and so sort of lightweight, to illuminate common structures between things. So when I was like doing my homework for this podcast, I read a bunch of stuff about like structuralism, and I need friggin' basic examples of categories, right? And so I watched a bunch of YouTube videos, right? And there was one by this neuroscientist who was again trying to use category theory for neuroscience, and he talked about something really interesting, was the spectrum inversion problem of what if you had someone who, when they looked at the colors, they looked at them inverted. So red would become green and everything, but not just one color, the entire all of it inverted, right? And you could have a conversation with this person and you would never notice it,
right? Yeah,
because who knows, like what the red that you see is the same the red that I see, that
when it's not,
right, exactly, right. And then his argument was that for what matters is that these two things are isomorphic, right? The both spectrum are isomorphic, because of any conversation that you have, you will not be able to notice it. It just kind of like disappears.
Oh my God. That I think is the best like definition of like the relationship is what we're caring about. Like,
and the relationships are all the same.
Yeah, exactly.
I've got a farther question, like this relation. Like, I'm going to give an example and you're going to tell me if I've said anything even remotely related to category. Like the cleanness of this, like this way of looking at the world and looking at like categories and situations are, you could look at like something in 3D space and you can say this relates somehow to a different way of mapping 3D space. So instead of like X, Y, Z, like cartagonal like coordinates, this is something on like rotational coordinates or something like that, and we can map this to a rotational position on Earth with latitude and longitude numbers that can be mapped together by interpreting these things these different ways.
That's definitely the kind of approach, right, of like translating one thing into another through a kind of transformation to see it in a different context, right? That's definitely the approach, right? But for like specific objects themselves, right, you don't need the full power of category theory. Category theory comes in when you're looking at like different areas of mathematics, right? When you're going from geometry to algebra. That's why it's so abstract, and that's the thing, like the kind of thing that you're talking about is what mathematicians have been doing, right? That's what they've been doing. But then at one point you went like, oh, no, this is too much. You're going too much into the stratosphere, and you're looking at the mathematics of mathematics, the patterns throughout the whole thing. This is why what other mathematicians think I do. They think I'm like in Alice in Wonderland. They think that it's, this is, you're going crazy now. But we view that, no, this is just what you do all the time in mathematics. We've just applied it to mathematics itself. You know, this is why it's almost like the mathematics of mathematics, you know.
Third question, I promise I'll stop then. At the beginning of your historical discussion, you talked about how back 300 BC, the Greeks were talking about, Romans were talking about like applying logic in proofs, like specifically in, I think you mentioned geometry. If I know two sides of a triangle and I know angles and everything, I obviously can figure out what the last one is, QED, right? And I like the idea that there's like almost 2,000 years where we're not doing logic. We're just figuring out calculus and algebra and all this other sort of stuff in our areas. And then we start realizing there's a connection here, and we can, you've sort of implied that logic suddenly took back up in the 1900s or the 19th century. And I like the idea that all of a sudden people are like, well, we need proofs again. We need to start dealing with them again. And we need to apply them to what we thought was holy in the first place, which is the fundamentals of math.
There was a few advances in like logic after, you know, Aristotle and everything. There was some guys in like the Middle Ages doing some stuff with quantifiers and whatnot, but the real breakthrough happened, you know, around the crisis of foundations, when Gottlob Frege sort of like came up with first order logic, or, you know, a formal system of mathematical logic, right, which was a formal language, you know, that he wanted to use. First is like, I need to clean up the language. We can't talk about mathematical objects with just normal language, right? Which is why it's so hard to come to this podcast and like, now I'm going to talk about this in plain English. The whole purpose of mathematics is to not talk about things using natural language.
There's
right?
centuries avoiding natural language.
Right. We're trying to put things into a formal language, right? And so there was this huge advance in like mathematical logic, you know, in the 19th century by Gottlob Frege, because he wanted to set up foundations of mathematics. His project essentially failed. You know, he wanted to first clean up the language. I'm going to do like, you know, formalize, well, it's first order, second order logic and everything. And he was then going to use this language to, based on basically the rules of logic, define numbers, right? But then Russell came over with his paradox and just crashed the whole thing. You know, I believe his book was like still in the printing press when he got the letter from Russell, and like, yep, no, sorry, your project is being completely derailed, you know?
So remind me of the Russell's paradox. Was that the set of all sets one?
Not quite. Jamie knows this one.
Yeah, no, it was because I think I told you that it was my favorite paradox from the class that I took on paradoxes. But it's basically if you think of a set of something, it is possible for that set to contain itself. It is also possible for that set to not contain itself, right? Like
what is a set?
Okay.
Tell me
like
this.
Group of stuff.
Okay. Just anything.
It's just like a group of anything, right? You could have the set of all natural numbers we were talking about earlier, like 1, 2, 3, 4, 5, etc. You could have the set of all cats. I just saw my cat going around somewhere.
So for instance, the set of all things that are not a cat.
Yes.
Think about that set.
Everything that isn't a cat also includes everything that isn't a cat. So it's inside of itself.
Yes, true.
Did you get that, Parker?
I think I get the first part. I don't get the part where something that like is then not a part of the set. So like, how could something that is not a cat not be a part of the set of things that is not a cat?
No, so the set of things that is not a cat includes everything that is not a cat.
Including the set.
Including the set.
Including this, okay.
Yeah, because the set of things that is not a cat is itself not a cat.
Which becomes promptly circular.
Okay, and now I'm following.
Yes, okay. So you have sets like that. You also have sets, I'm trying to think of a set that does not include itself. So I think like the set of all natural numbers would not include itself because it's not a natural number, right? It's a set. It's not a number or an integer or whatever you want to call it. So you could think of the set of all sets that do not include themselves and whether or not this set includes itself. So if that set
Hold on, say all of that again.
So you have a set, a big like umbrella category, and underneath that category is all other categories that do not include themselves. So things like the set of all natural numbers doesn't include itself. It would go in this set. Other sets that are similar to that set would go in this set, right? And so this set you think like, oh, the set of all sets that doesn't include itself.
Does that include itself?
Yeah, if it doesn't include itself, if it's not in this set, then it ought to be, because as soon as you put it outside of the set, it's a set that doesn't include itself. But then as soon as you put it inside of the set, it includes itself.
The instant you said that sentence, things clicked for me. I understood why this is a paradox.
That very last sentence is also where mine clicked.
Everything until then. I was just getting...
It can't belong. It has to belong, but it can't belong.
It's like constantly just bopping back and forth between belonging and not belonging. And so Russell was like, to this other guy, hey, fuck you, this destroys your theory.
in like mathematical notation, it's so easy to describe Russell's
I just
set.
took like 5 minutes to
because you say it's a set that satisfies, of all things, that satisfies X does not belong to X, right? So X, you call the set R because Russell, right? And to belong to R, X does not belong to X. It needs to satisfy that. And then you ask yourself, does R belong to R? Well, if and only if R does not belong to R, right? So that then it's like, yeah, it belongs to itself if it doesn't belong to itself, right? And it's really clean. You know, I'm saying it's not clean when I say it, but
after that 5-minute explanation, you saying that in 10 seconds almost
But when
works.
you see it on the blackboard, you're like, aha, boom, right?
But yeah, so I think that the interesting thing too about this like nice, clean mathematical notation is that you just front load all of the effort of understanding it. You learn the notation and then you can write things in nice, clean notation. But when you come in like in the middle and you try to explain it, you have to also explain all of the work that went into getting there.
This makes math and higher level maths have a double purpose of like they immediately create their own secret societies. No one can understand what's in it without a couple of years of in playing English training.
No, for sure. And I think, you know, at times you gotta sit back and like really try to figure out, you know, what it is that's going on, right? It's really tempting to just, a lot of times, just sort of let the notation do all the thinking, you know, especially when you're, you know, in kind of like school. And by that, I even mean like grad school, or like I need to prove the theorem, blah, 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 and you don't really understand what's going on, you know, so, you know, sometimes you need to like take a step back. You know, it was actually at one point like this was advice given to me by Martin Hyland, you know, who was Eugenia's supervisor. You know, at one point I had like, you know, I was kind of like stuck in my PhD thesis, and I had like this huge diagram, and sort of category theory is all about like drawing these diagrams and arrows, and Martin Hyland, who's like the patron of category theory, he said, sometimes I don't care about the diagram. And I was like, what? And I'm like, yeah, you know, if you don't understand what's going on, you can be sort of spellbound by the notation, right? And just, oh, the notation works, and you know, without trying to understand what is really what is the intuition behind it, you know. So I think you gotta kind of like bounce backwards and forwards with that, you know, of like, sure, we've got a clean notation, but clean notation is good for calculations. Make sure you don't understand what it is behind what you're doing, right? Have the intuition, right?
I find that fascinating because I found multiple times going throughout math classes in undergrad and even before that, if I'm being honest with myself, that let's take calculus, for example. A huge part of calculus 1, if I'm remembering correctly, is bringing you up to the understanding of what a derivative is, right? And once you get there, you get a notation for it. Like you take all this time to figure out what it is. You're taking the limit as it approaches infinity of something over something else and all this sort of stuff. And you literally have weeks, depending on the length of your class, to learn what this is. And then afterwards, you get a nice, like, a symbol for it. Yeah, like, d over dx, right? You've got the symbol to represent it, and you're expected to do it almost automatically after that fact. And similar with, like, the opposite of a derivative, an integral, and so many other things afterwards, you take the time learning what it is, you get the symbol for it, and then you sort of forget what all the processes to, like, do that symbol are. And I can imagine in category theory where you are talking highly abstract, like you take a look at all of these symbols that you have on your page. Like I was looking at where we ended up towards the end of this book, and it's impressive and scary. And I imagine it's really easy to miss the forest for the trees. So yeah, I think sometimes you just gotta like
really try to think intuitively of what's going on. Like, because sometimes even integrals is a good example. Sometimes, now I've got like this method for solving this problem, right? But a lot of times you look at an integral and you're like, this is just the center of mass of a sphere or something like that. You can just solve it through geometric intuition, right? Instead of just like, oh no, I'll look up the integral on the table and then try to do a bunch of manipulations without trying to understand what is the object that's underneath it,
Should we get into the book?
I did read the book. Well, because the book doesn't really do, at least not the portion we read, doesn't really do math. No. Right? So it talks about the concept, and then it uses like the particular one it uses is like the mother of your mother is your grandmother. It's kind of, so it's like the A goes to B goes to C, so now A can go all the way to C. So like creating that relationship. So I'm not sure that I understand how that translates to numbers and math necessarily. So I understand that it's comparing one thing to another and creating the relationship.
Yeah. So, like, the prototypical example of like that I like to use is again like the natural numbers, and like take the two sets of natural numbers, the one that I like and the one that some other people like. So one starts from 0, the other one starts from 1, right? If you look into each of these sets, they have a first element. One is 0, the other is 1. When you look at it categorically, you see like, we have a name for this. This is what's called an initial object. Categorically speaking, these two are the same, right? They have the same structure. Not only that, when we look inside them, the number 0 has the same properties inside that set as the number 1 has. It's like the first one. You get me?
So what you mean? So what you mean by like the relationship is one is each one more than the next.
One's like translated over.
So regardless of whether you start at 0 or start at 1, we agree that 1 is 1 more than 0 and 2 is 1 more than 1.
Yeah, exactly. So the one that you start with from 0, you have 0, 1, 2, 3, 4, 5, right? And the relation, or as we say, the arrow goes from 0 to 1, then from 1 to 2, then from 2 to 3, so on and so forth, right?
So how does the arrow then start going from 0 to 2? Because that's a completely different. So whether I count by 2s or 5s, now that I count, 5, 10, 15, but then you create an arrow from 10 to 15 or 10 to 20, and like the relationship, it feels like, would break down at that point.
Gotcha. Yes. So it's because to have a category, your arrows, right, your relations need to be able to compose, right? And this is what we call composition, right? If you have, which in this case is just a transitive property, right? Because what does the relationship say? It says that it is smaller than, right? So 0 is smaller than 1. And if 1 is smaller than 2, then 0 has to be smaller than 2.
So it's not about how many digits it's away. It's about it still maintains a size difference.
Exactly. Yeah. Okay. It's just saying the relationship between a number and another one is smaller than, right? And so you start with the increments of 1, and then you can compose them to say that 0 is smaller than 10, right? And so that's what's called arrow composition, right?
Because 0 is smaller than 1, you also know 0 is smaller than 2, and you know that 2 is smaller than 3, you have to know that 0 is smaller than 3.
Yeah,
right.
Exactly.
Adding them all up.
Right. Okay. And so the relationship is a mother of doesn't compose, right? Because you go from you to your mother, and then your mother to their mother, right?
You jump from daughter to grandmother.
Right.
It's
not the relationship, that one doesn't compose. If you just say is a mother of, that doesn't compose. You can't form that category. But you could say is a descendant of, then that does compose, right? If you loosen it up a bit, or am I going in the right direction here? Yes. If A is a descendant of B and B is a descendant of C, it will compose, right?
So it actually helps it to be more vague. Like,
yes,
the more vague something is, the more you can
Well, helps it is an interesting term because if your end goal is to make a category that contains what you want it to contain, yes. But if you want it to contain something interesting, being more vague only gets you so much information.
Yeah, you gotta see the trade-off there, right? The categorical approach has, the proof is in the pudding. It's being applied everywhere. It's gotten it's described so many things, right? And we found that this compositional relation is the crux of it, because here's the thing: if you take out the compositional relation, it's just graph theory. And graph theory, sure, it's awesome, it's cool, but it did not redefine mathematics. Do you get me? It's just essentially that is the definition of a category, right? It is a category, something with objects, which we call the dots, the points, or we call them objects actually, and arrows between those objects, right? In such a way that you can have more than one arrow, so it's a multigraph. They have a direction, it's a directed multigraph, right? And you can compose the arrows, right, to create a new arrow by composing that. And the composition is the thing that we didn't have before in graph theory, and it encapsulates a lot of the structure of functions, because functions also compose, and so much of mathematics is done through functions, right? And relations, transitive relations, also compose, and so much of mathematics is done through transitional relations,
Something I noticed in the very last section that you had us read is that they start labeling the arrows between, you start off with A is related to B is related to C, and you do the transitive stuff that you were talking about. And then they're like, okay, well, these arrows don't necessarily need to be the exact same relationships. They label the arrows F and G. And then they do the same basically operations to F and G that you did to A and B and C. It's just on the next level up. And so it's really graphically then depicting the meta-ness of how it's not just describing the data, it's also describing the relationships between the data in kind of the same way that it's described.
We actually don't care about the data anymore, if I'm getting it. The relationships are the interesting part.
It's the scheme, right? Because again, when you look at natural numbers with zero, natural numbers without zero, they're different, right? But 0 in 1 has the same properties as 1 in the other, of being the first, right? And it's something that can be described categorically, right? It is the first one, right? But also, we're just looking at one element. We can also look at the entire set, and these two sets are what we call isomorphic. They have the same form, essentially, right? If you start looking at the labels that you put on the elements, these have the same form. And you can go even a step further, right? Which is now we looked at the natural numbers, these two different sets, as categories. Then we looked at them inside the categories of ordered sets, right? And established that they are isomorphic, right? Now we can go even further and describe what a set of natural numbers would be using the language of category theory. Okay. Instead of just taking a set that I've already built, because okay, fine, you've established that these two things have a form, right, the same format, but they already existed, right? Well, I can even give you a way to construct them using just the category theory language, right? And this is what's called a natural numbers object, right? I'm going to describe the behavior just using arrows and relationships with other sets around them, right? So is that, anything that fits that description is going to be isomorphic to the natural numbers that right?
That is weird to me. Weird.
Sorry, it went really abstract now.
Yeah.
I need to ask. So you are only describing you're not describing the relationships between the data points in the set. You're even beyond that. You don't care about the data. As we said before, you're doing the relationships that each point would have to other things outside. So help me.
Yeah, this is stuff, right? Let me try to think of natural numbers is maybe a difficult example, right? Because I don't have a blackboard right now, right? But for instance, so when you take the product of two sets, right? You know, you usually do this with like real numbers to get like the Cartesian product, right? You know, when you take the product of two sets, you get another set, right? Which is the product of you could take the product of, you know, the real numbers times itself, and you have the usual Cartesian plane. If you don't want them to fill up, you could have taken the product of the integers by themselves, and you'd have like this weird lattice of points, right? You know, you could also take the product of more complicated structures as well. Like, for instance, take the product of two circles, okay? You would get a donut out of that. You would get a torus out of that if you took the product of two circles, okay? Because think about it for a second. What is it to, you suppose your donut had coordinates, right? It would have coordinates along sort of one sort of axis, kind of, and then another one. Try to think.
Okay, so it's just like circle, 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 around it in a circle, and that's a donut.
As though you were taking cross sections of the donut.
Yeah. There we go.
Yeah.
To then put them all together like little, you know.
Exactly. You're getting like rings, which are the cross sections, and then you're putting them together around a circle, right? So you took the product of a circle with another circle, right? These are all the same categorical operation, right? But being done in different objects. Do you get me? And you can have a description, a categorical description of this operation, which I'm not stating right now because it involves universal properties, but trust me.
You can do this.
You can do this, right? This is what's known as basically a product in a category, you know?
And you then be relating all those things that we discussed, like the different ways of plotting these things together. That's the relationship that you're... Okay. Wild. I do want to take it back to the book, though, because this whole field of mathematics is like exercise in like thinking differently from everything you've done in math. But in a way, I feel like, and the author of this book clearly agrees, she says right at the beginning, this book is for literally everyone, even people without a serious math background. Usually you don't learn about this stuff until you've learned all the core fundamental introductory parts of math, and you're sort of brought together into this mega like postgraduate study, which now becomes this theory. And she's like, this fucking sucks though, because without any knowledge of math, you can still apply logic. As you said earlier, it's applying logic. And I did really get the sense, even in the short bit of reading in this book that we did, that it really is just a logic course. If you can ignore some of the math notation, you can ignore the feeling that I shouldn't be able to do this, you can actually understand some of the stuff that's going on. You just have to practice thinking abstractly.
Yeah. It's I think it's a lot easier for mathematicians though, because it's almost like everything's kind of like just ready, you know. It was built, it's a language that's being designed to be put on top of mathematics already, you know. But people have been applying it to like neuroscience, you know, and I'm like, whoa, okay, you know, and I don't know how exactly, you know, but that's the challenge of the new fields of trying to get this language and apply it in different ways, you know.
So are you always having to like define the direction you want to move in, or would all of the arrows technically need to be double-sided arrows at all times?
No,
if A goes to B, then logically B also goes back to A.
Not necessarily, right? So that's the thing. Usually they only have one direction that they go in.
But are you defining that? So when you go to apply this to something, you're defining the direction you want it to move in.
Yes. Yeah.
And the reason is why it might go in one direction, if I can speak on a book that I've spent 2 hours in. A goes to B, as you just said. Well, that goes to is the relationship, and that goes to could be A is less than B. That makes sense, but if you turn it around, A is greater than B and A is less than B can't both be true. So like that goes to is the relationship, which as we've said before is like everything we care about in category theory. You care about, not me, not inclusive.
Yeah, I guess it just means that you can easily flip it. So 0 is less than 1. You don't have to redo all the math to then justify that 1 is more than 0 if you've already established 0 is less.
Yeah, exactly. Yeah. And there's actually an operation for flipping over all the arrows called taking the categorical dual, because they thought, ooh, okay, we have a category here. What happens if you flip over all the arrows, right? Now you you invert all the theorems. Do you get me? And then we usually put the word co in front of something. It's like now products become co-products, limits become co-limits, and that is just part of the sort of like lingo of all category theorists, like just putting co in front of something when you've inverted it,
Oh,
no.
so you're not actually doing the math of whatever the fuck a co-limit is. You're just saying this is now a co-limit.
Yeah, exactly. And so first of all, you get a bunch of theorems for free, right, involving the inverses, right?
Yeah.
And you got a bunch of like stupid puns as well. Like, I'm not putting my car in reverse, I'm putting it in co-drive. And what is a mathematician? It's a machine for turning coffee into theorems. What is a co-mathematician? It's a machine of turning theorems into phi. Because if you you go back to the same thing.
Yeah, I got it.
Okay, now I'm getting it. That's terrible.
Yeah, so here's another interesting example of a category that's slightly different from the usual order, right? Which is now, instead of saying that a number has an arrow to another number because it's smaller, but let's say that a number has an arrow to another number if it divides that number. So for instance, 2 divides 4. So you put an arrow from 2 to 4.
And that means that evenly you've got 4 divided by 2, there's no remainder.
Exactly, no remainder, right? Just natural numbers, right? Before, in our previous category, when it was just less than, right? 2 is less than 3, but 2 does not divide 3. So in this new category, you don't have an arrow, right? You do not have an arrow from 2 to 3. You have one from 2 to 4. So this one has fewer arrows, basically.
In this category where you're checking both, right? You're checking that it's less than and it divides.
No. This one just
divides. Yeah.
Right.
Okay.
And so you start getting some interesting things because, first of all, like 1 is still, in some sense, the initial object because it divides everyone, right? It's divided. But now, you could, if you're a bit hand wavy, have what we call a terminal object, an object at the end, which would be 0, because everything divides 0. Right, 5 divides 0, etc.
You just blew my mind by putting 0 at the fucking end.
It's okay. There's a little problem there because does 0 divide 0? Right, but you get the idea that you have like a different category, right, with where you're going by divisibility, right? And the interesting thing is that now, if you take and pick a number, and if you just don't tell me what the number is, but just give me the arrows, I can reconstruct that number. You get me? By knowing everyone who divides it. You get me? You can reconstruct that number, because you can basically, it's going to take a little bit of math, right? But you're going to have to figure out who are the primes in this system, figure out who are the powers of primes, and, you slowly build up the number that you had before, right? So it's interesting how in this category, all the information that you need to build a number, you don't need to look into the number. You can look at the relations that it has with other ones, right? And it's a non-trivial category as well. The one that we had before where it's just less than, you can also do that, but it almost feels like cheating.
Right.
If I tell, 1 is smaller than that, and then 2 is smaller than that, and 3 is smaller than, but not 5. Which number am I talking about? It's kind of dumb, right? But the one that's just like division means that, you can recover what the original object was just by looking at the relationship with different objects, right? And that is kind of the categorical approach. What the thing is in itself doesn't matter. What matters is the relationships, right? Or you can reconstruct it through the relationships, right? If you have sufficient structure. Does that make sense?
That kind of sounds how like astronomers find stars or like planetary bodies. Is that like you can't always see it, but you can see other shit that's like orbiting around it, or like how light is bent by it. And then you're like, oh, there's something there. We don't really know what it is, but we can like kind of back ourselves into understanding that there's something there.
Yeah, for sure. Yeah, no, that's a good example. Yeah. It's interesting how you can translate like different constructions that you can do in these 2 categories, right? So for instance, you can, in the category of where things are just ordered, right? You can try to take a categorical product. Remember that I was taking products before? I took the product of like two circles, etc. You know, if you think of natural numbers as being ordered, you can try to take the product of two numbers. What would that look like? You know, in terms of category theory, that looks like it's the taking the max of them, of both, the one that's greater than both of them, right? Because that's how you define a categorical product of two things. It's a thing that is above them, that has arrows pointing to it, but it's the smallest one that has arrows pointing to it. Okay? You know, that is the I defined a co-product there. Okay? A product is the other way around. You know, a product is something that's underneath them, right? You have two things and the product will be underneath them with arrows going into them. That's what a product is. What is that in the case of the product of two real lines? It's just the projections, right? Those are the maps. The maps are the projections, okay? And so it's just, you know, you take a product of a real line with a real line. What do you have? You have the Cartesian space, right? And you can project from the Cartesian space onto the real lines, okay?
That went way over my head.
In natural numbers with an order, right? If you take the two numbers, you take the smallest of the two, right? That is going to have an arrow going up into each one of the numbers, right? Because it's smaller than both, right? In the category of numbers where you using divisibility as the arrows, you're taking the greatest common divisor now. And that these two examples have the same categorical structure, right? Because like I said, I started with two numbers, right? And I want a number that is underneath both of them, right? You know, when it's just the order, you take the smallest one, right? But when it's divisibility, it also has to be divisible, so you take the greatest common divisor, right? So that's kind of the example of a similar kind of structure in two different categories, right? And these, we call them products, right? Because when we look at sets and functions, you have the product of two sets is just that Cartesian product, and the functions are just the projections, right? Which, okay, it's hard to follow, but just trust me.
Explain a Cartesian projection.
Yeah, I'm getting lost on this.
That's the dot on the map.
I think that's the thing that's missing, right? You don't know what like the Cartesian projections are, right?
No.
So it's basically, you know, when you do a drawing on the plane, right? The projection function just looks at its shadow. Did you get me?
Okay.
Right. So you have xy, right? The projection function just looks at its shadow on x, and you have another projection function that looks at its shadow on y. You know, these are the projection functions.
So think of like a curve. Imagine any curve, and its shadow on y is how high that it goes up on y, but just on y. And its shadow on x is how far to the left or to the right it goes on x, but just on x. There's no height on x. There's no height on y.
They don't care about each other.
No, I don't think so.
Yeah. And but all these things categorically have the same structure, right? Because one hand I looked at the category of natural numbers and the arrows are just is greater than the other one, natural numbers and divisibility. And now for the most complicated example was the category of sets and functions. Right, that's why it's so complicated, because this is, you know, I haven't introduced this category yet. It's sets and functions, which has a lot more structure, has a lot more wiggle room and everything, you know. So you're taking the product of two sets, and then your functions, you know, from this product going into the two sets that you had before are the projection functions.
By set, do you just mean like a set of all rational numbers, set of all numbers that are divisible by two, that sort of thing, sets that you define, or is there some other term for this?
So you can do it with any set.
Any sets, yes.
So you can do this with any objects in the category of sets, right?
So, okay, so if we go back to our circle that we multiplied and got a donut, like if you do functions inside of the donut, you can, like, the projection functions are like what that would look like on the circle that you started out with.
So
kind of, maybe.
So the projection functions for your donut would just take the coordinate there. Do you get me? Because think of a coordinate system on your donut, right? Yeah. So you have the ring that's the vertical ring, right? You can think of, just coordinates there, just like you have coordinates on Earth, right? And you have the other ring as well going around, right? You can think of coordinates as well. There, the projection functions, we just take the coordinates. It's almost like too simple, almost. You're expecting something more from it, but that's the thing. It's just a simple categorical description of something, right? That's unifying.
Are categories always like ordered in that like things inside the categories are like bigger or less than other things, or like
No, so that's the thing. So this is one thing that I asked like all my colleagues, like, hey, can you guys give me a really basic example of a category that's not just a friggin' pre-order? And they're like, no, sets and functions, maybe.
So something that interested me about how Eugenia like set up this book before she started going into the math was talking about how everybody thinks math is super rigid and it's all like these definitions, and she's like setting up all these rules for yourself and constraining math in certain ways is kind of like in real life constraining things like who can get married to whom, right? And talking about, and I can kind of see like if category theory is just going like, oh, well, if we have this function, why can't we apply it to this thing over here? I can kind of see like where she's coming from, where it's like, okay, if we want to remove restrictions in real life, we should also remove restrictions on how we're thinking mathematically.
Yeah.
Is that kind of like where she's coming from? Like, do you have other examples of like her taking this interesting like parallel between math and real life in terms of like removing restrictions or something like that?
Yeah, I mean, almost like the ontological history of math is just like people going like, let's try to do this even though people say we can't, So for instance, we have like negative numbers. Just think about that for a second. Negative, what does that mean? For
you don't have negative cows in a field.
Exactly. Right, exactly. And so when the sort of West, when zero was brought over to the West, people were like, no, can't have the number zero. No, this is demonic. No way. What does this even mean? It's the absence of creation. It's the devil. And in negative numbers, we're taught this stuff as if it's like the most natural thing. It is not. It is not the most natural thing. It doesn't exist. We're kind of okay with it because we're used to it, right? But then when you look at like, complex numbers, imaginary numbers, people go like, oh my God, this is so nuts. It's just as nuts as negative numbers, man. You're just going in a different direction, So the sort of like the history of mathematics has been like a lot of times the history of people just like relaxing ontological requirements of like, does this exist? Who cares? Let's just define it as if it does exist and then keep going, right? The thing that got me interested in my actual area, which is inside category theory, is topos theory, is when they started doing this to logic. Let's start weakening logic to see what we can get away with.
Whoa.
For instance, let's see the law of excluded middle. How much can we tweak that and still make some sense?
What is the law of excluded middle?
So it's saying that something is either true or it is false. There is no in between, right? And the thing is, for a lot of computer scientists, this kind of approach is meaningless.
Yeah.
Because there's the whole thing of like, it hasn't finished computing yet. There's no space in my computer to run the algorithm, so I don't know. Right? This thing of, yes, but it's either going to be false or it's going to be true. Yeah, sure.
False, true, or pending.
Exactly. Right? Exactly.
So when you say it's meaningless, like it's so obvious that there's something else here that it's meaningless. Yeah.
Right. In the sense that it's not a good way to model the reality with which you're working. Right. And there's also all kinds of like fuzzy logic as well, where you have maybe you can give like, true is 1, false is 0, and let's suppose there's a spectrum in between there, of certainty, right? And so those are the things that I found interesting, because if you take out the law of excluded middle, put in things which are slightly weaker than it, you can start doing mathematics that is a lot more constructive, because a lot of the times when you use the law of excluded middle, you cheat in mathematics. You do, I don't know if you've seen proofs by contradiction. You prove the existence of an object just by showing that its non-existence would cause a paradox.
Huh.
Okay?
Huh.
But then you haven't told me how to construct this object. You just show that it not existing would cause a paradox, but I want to know how to build it. And you're like, nah, sorry. You know?
That's some other
But isn't
paper.
that kind of what you were saying about like space? Like you have to accept that something is there because the light bends around it. And that same like
Gotcha. And so the thing is, you know that there's something there, but you haven't told me what it is. Do you get me? It's a little
So
bit
now
like,
you're asking too many questions.
yeah. Right.
It's more like the either 1 or 0, but there's nothing in between, can only get you so far. And you need to start accepting the squishy in betweenness if you want to be able to say anything about what is there.
Because the thing is, I'm very much a pluralist in the sense of like, if you want to take classical Aristotelian logic, I'm like, yeah, sure, that seems to be like the logic of the real world, right? As long as you don't get too quantum about it, the cat is either alive or it is dead. Of things that I see and stuff like that. But when you take into account, mental processes in construction, right, or literally, computer science, the science of computation, of calculation, right? That binary is just not a good way of dealing with things, because there's a lot, because you want when the requirement for something to be true means that you know how to construct it, the law of excluded middles seems lacking, basically, will lead to you to get to conclusions that are empty. Like, sure, this exists, but I need to know how to build it, And there's lots of examples in mathematics of things which are not constructive, just through Jedi mind tricks of like, let me see if I can remember here. There is one example which involves playing chess where each person makes 2 moves instead of just one. And the argument is that White has a non-losing strategy that they're either going to win or draw. White has a non-losing strategy.
Guaranteed?
Yeah, guaranteed non-losing strategy. And you go say like, nope, that's not true. Let's assume that Black has a winning strategy. Okay, because what would be the opposite of a non-losing? I mean, the opponent has a winning strategy. No, Black has a winning strategy. Oh, does Black have a winning strategy? And is Black the second player? I'm going to move my knight forwards and backwards. Guess what? Now I am the second player. You get me? Now Black is going to move and I'm going to reply. So that's called strategy stealing, right? So I've just proved to you by contradiction that White has a non-losing strategy. What is the strategy? I haven't told you what it is, but I just showed that, if it doesn't exist, you get a paradox, right? So this is like strategy stealing, basically, this name of the argument. And it seems like I just did a Jedi mind trick here, but it involves the law of excluded middle of saying like, if that you go from a not non-losing strategy is a winning strategy.
Once you step away from true or false, you can then bravely stand in the middle of that Jedi mind trick and say, well, this doesn't matter.
Right? Yeah, exactly.
So how much does math care about, like, does it also care that it can't do things? So you said that a lot of it is like somebody being like, oh, you can't do that. And then you like mathematically trying to do it. Does math also care that at the end you couldn't do it?
So, like, the most monumental result in mathematics was, like, I would say it's Gödel's theorem, saying that you cannot find a mathematical system that can prove its own consistency. And no mathematical system, and every mathematical system that is consistent will have things that it cannot prove. There are always things that are outside of its grasp. And guess what? One of those things is its own consistency.
No universal theorems for mathematics.
Let me drill down to this. By system, you mean like calculus, algebra?
Yeah, so a mathematical system based on like actually, it has to be sufficiently powerful to contain arithmetic.
Mhm.
You know, a formal mathematical system based on like formal logic that is sufficiently powerful to contain arithmetic cannot prove its own consistency. If it is consistent, it cannot prove its own consistency. You know, and so you're literally saying, because this was Hilbert's program for the crisis of foundations. Like, yo, let's clean up the house. Let's put everything in first order logic, formal logic and whatnot. Let's try to set up mathematics ultra formally, and then let's try to mathematically prove that mathematics is consistent. Like the snake is going to eat its own tail somehow. We're going to prove it, right? We can do this. Because come on, mathematics is consistent. And then Gödel enters the chat and ruins everything. Say like, no, I'm going to prove to you guys that, any system that is consistent and sufficiently strong to be able to have arithmetic in it will not be able to prove its own consistency.
I kind of like to end by like asking about, the coolest or most interesting thing that you learned, or like something that you're going to take away from this conversation.
I feel like I can start out with something. I think the most interesting thing that I learned was not about the category theory here. It was generally the sense that these higher level maths are a logic puzzle more than they are any like a memorization puzzle, like your times tables or anything like that. And that made me infinitely more interested. Like 6 pages into this book, I was already hooked. And I know I'm going to go back the next time I have any free time, whenever that exists, and read through. Because when I was getting an engineering degree, the thing that endeared me to it was the fact that you're learning some fundamental principles of engineering, but when you get to it, it's actually logic. And I think everyone benefits from just testing their brain, bringing into a strange space and seeing what can I figure out from this space. And I think that this book is a great read for anyone listening in the audience. Get through chapter 1. You'll like it. Get through chapter 7 and 8. You'll like it. I can't speak beyond there, but I'll get there soon.
I mean, I think I still come back to, like, I just never thought about math being a conversation about how things related to each other.
Yeah.
Like, that's kind of blowing my mind. Just like, it's just like, I always thought of it more as like just a set of things we all agree are true. And that is not it.
So Bertrand Russell had this quote saying, mathematics is the subject matter where we don't know what we're talking about, nor if what we're saying is true.
And and I always thought of math as just like concretes of this always equals that if you did it right.
No, it's that's the thing. That's the interesting thing, that it's way more fluid and has a lot more room for creativity and expression and just exploring weird shit.
All right. Well, the book's called The Joy of Abstraction.
Yes, it's by Eugenia Chang. We have been talking with Will Lima, Nick Max Wolslegel, and Parker Kraft. And I am Jamie Moffa. Our music is by Sam Brunwasser. You can find more of his work at soundcloud.com/visualsnowbeats. As always, you can download the paper and read the transcriptions at inplainenglishpod.org. And make sure to follow us on Twitter, Facebook, and Instagram at Plain English Sci. That's PlainEnglishSci. Thanks again for listening, and we'll see you next time for another episode of In Plain English. I kind of really want to go get a donut.
We should have gotten donuts for this episode.
Brendan, can you go get us some donuts?
This is our 50-50 hindsight moment. 2020? 2020.
50?
Hindsight's 50-50. That'll go in the blooper reel for sure.